Hello, y'all. Welcome to lesson 61 of my DP chemistry curriculum. Today we're doing structure 3.1.5. We're going to continue with the metallic and non-metallic properties in a continuum. We're going to be specifically talking about the basic metal oxides through amphoteric to acidic non-metal oxides. We're going to deduce equations for the reactions with water of these oxides, as well as with carbon and sulfur. And we'll talk about acid rain and ocean acidification via these oxides and their reactions. So we previously discussed that metals and nonmetals represent a continuum in their bonding as well as in their properties. So what we're going to specifically talk about here are these structures and the structures of elements and oxides and how they also represent this continuum. The reactions of oxides of these elements is one of the things that the DP really likes to go over and show that you can notice its transition. So the first property we're going to be looking at is the acid-base nature of oxides. And we'll see that they create this continuum. But for that, we have to know that acids, generally one of the definitions we use, we'll get into it later when we talk specifically about acid-base chemistry, is that these produce H plus in water. So when it becomes aqueous, they form H plus ions, while bases, on the other hand, produce OH minus ions in solution. And then furthermore, because we're talking about acids and bases, we're going to use the pH scale, which as far as what you need to know for this, it starts at 0, goes to 14, and then right in the middle we have 7. 0 to 7 is acidic, 7 to 14 is basic, and right in the middle is neutral. And the more you go towards 14, the more basic it gets. The more you go towards 0, the more acidic it gets. So this is what we need to know. So as we begin to explore this continuum, we're going to specifically look at the period 3 oxides. Period 3 oxides. As they're going to show us a trend. So we have quite a few of them. We start off with sodium oxide, then magnesium oxide, then we jump all the way to aluminum oxide, then we go over to silicon dioxide, then we move over to phosphorus oxide, which would be tetraphosphorus decoxide. Then we go to our sulfates, SO2, SO3, and I did not leave myself enough space, so I'm just gonna scooch these over. And we're gonna end up with Cl2. Oh, all right. So as we look at these, we have 3 distinct categories right here. We have a division between sodium, magnesium, and aluminum. Then between aluminum and silicon, we have another division. And so when we look at these, a couple things of note is these are generally basic, meaning they have a pH of greater than 7. Aluminum oxide is amphoteric, which means it can be above 7 and below 7 depending on the conditions. So as a powder, it is basic, but in solution, aqueous, it's acidic. So it can act both as a base and an acid. Now, the rest of these non-metal oxides are going to be all acidic, meaning they have a pH less than 7. So we have this continuum of basic, neutral, acidic. Furthermore, we need to understand the reactions that happens. So we'll look at some basic reactions. When we have sodium oxide or magnesium oxide, and we react with water, I'll do 2 different ones because they make slightly different ones. I'll do one, H2O. Sodium oxide makes two sodium hydroxides, while magnesium oxide makes magnesium hydroxide. Both of these are basic because they will dissolve. So this one will split into sodium and hydroxide. This one will split into magnesium and two hydroxides. And these are all going to be acidic. We'll keep our state symbol. Or sorry, these are all going to be basic, but they're going to be aqueous. And this will be in solid form. So these are our basic reactions. This is a reaction that you should memorize for your DP exam, as it will very likely come up. This also, by the way, works with any other group 1 metal or any other group 2 metal. You can pretty much do the same thing. So potassium or calcium, whatever. So you need to be able to do it with any of them. We'll move into our acidic ones. And for the acidic ones, there's only a few that you need to absolutely know. And we'll explain why you need to know these in just a moment. But you need to know carbon dioxide with water, which will be a gas. They'll all be with water, so I'll just wait till the end. You need to know sulfur dioxide, gas with water. You need sulfur trioxide, gas. When we react these with water, which the most common place to react with water is either in the atmosphere or in the ocean, we get three different equations. For carbon dioxide, we're going to make carbonic acid, H2CO3, aqueous. For sulfur dioxide, we're going to make sulfurous acid, H2SO3, aqueous. And for sulfur trioxide, we're going to make sulfuric acid, H2SO4, aqueous. So these are the reactions you definitely need to know for the DP exam. Now, the reason you need to know them is due to their implications in nature. So we're going to go over these individually, implications. So specifically, acidic nonmetal oxides will lead to two things. So they lead to acid rain and ocean acidification. Now, these are two things, acidification. These are two things that we often associate with fossil fuel burning and global warming and climate change. And these are direct consequences of these actions because we'll see how we make these chemicals. So we're going to start off with ocean acidification, even though I wrote that 1 second. If we look at the reaction that we're going to be talking about with this ocean acidification, it comes from the accumulation of carbon dioxide, CO2 gas in the atmosphere. Now, we produce this through combustion of fossil fuels. Well, we get it through combustion of almost anything. In fact, we exhale when we respirate carbon dioxide through combustion of glucose in our body. But we mostly get it through combustion of fossil fuels. That's the big turning point of where we started producing too much carbon dioxide. Now, what happens is the CO2 dissolves in the water of the ocean. And then it reacts to become carbonic acid, H2CO3. Now, that carbonic acid will then do things like react with seashells, react with mollusks. Whoops, didn't spell that one right. Mollusks, maybe, and coral and seashells. It will react with anything that's calcium carbonate, and it will dissolve these shells. And so it's very harmful to our sea life. It's very harmful to our ocean ecosystem, and it's going to have lasting consequences. So we need to understand that ocean acidification is pretty much a direct result of our combustion of fossil fuels, which then reacts with water to become carbonic acid. So that is the first one. The second impact that we're going to talk about is acid rain. So acid rain is specifically going to be via sulfur and nitrogen oxides reacting with water in the atmosphere. So you can think of water pretty much everywhere in our atmosphere. I mean, clouds are made of water, right? And so these oxides can react and form sulfurous or sulfuric acid, and nitrogen oxides will even form nitric acid or nitrous acid. So we'll look at that reaction as well because we didn't do it in this first one. Um, so they react with water in the atmosphere and become acids. So specifically, where these come from is sulfur and nitrogen oxides are products of, once again, fossil fuels. Fossil fuel reactions. So they're not direct products of fossil fuel reactions, they're associated products. So specifically, the sulfur is usually going to be mined, and we have impurities in fuels. So when we mine things like coal, we're going to end up mining a lot of sulfur as well, and that will be combusted and released into the atmosphere as sulfur dioxide or sulfur trioxide. Nitrogen, on the other hand, is already in our atmosphere, and what happens is it becomes nitrogen monoxide during combustion, and this will very easily become nitrogen dioxide through reactions with oxygen in the atmosphere, which will then become HNO3 in the atmosphere as an acid. Now, one quick thing that I didn't really mention before, but one of the reasons we know these are all acidic and release H plus is because they all start with H. Acids usually start with H, and the H's that come in the beginning are H's that can be released. You might then go, well, what about water? Water starts with an H, and water is in fact an acid. It can release H plus in solution to become H plus and OH minus. So it's actually amphoteric. It's both an acid and a base. Anyways, the big deal here with acid rain is, of course, it impacts crops, forests, mammalian respirations, and other animals. Respiration. And then it also moves out back into the ocean and also impacts aquatic life. So ocean, streams, rivers. So both of these are acid rain and ocean acidification are big problems that come out via these nonmetal oxides that get released into our atmosphere and then either react with the ocean or react with the water in our own clouds and atmosphere. So I hope this helps you understand this continuum a little better, the acid-base structures of these oxides, and have a great day.